Quantum teleportation of information between distant qubits can be thought of as a magical way to send a precise piece of information instantly, regardless of the distance, using the power of quantum mechanics. Imagine you have two special enchanted marbles that are magically linked. Whatever you do to one marble affects the other instantly, no matter where they are. If you change the color of one marble, the other marble will change to match it right away, even if it's on the other side of the galaxy. This is similar to how qubits and quantum teleportation share information through entanglement. Another example is like having two perfectly synchronized clocks that always show the same time, no matter where they are. If you set one clock to a new time, the other clock will instantly reflect that change. The connection between the clocks is so strong that it seems like the information travels faster than the speed of light, even though no physical signal is actually sent. This instant synchronization is akin to how entangled qubits and quantum teleportation share information. Consider also a pair of magical mirrors placed far apart. When you make a change to the reflection in one mirror, the same change happens to the reflection in the other mirror instantaneously. The trick here is that the mirrors are linked in a way that ensures they reflect the same changes simultaneously, just like entangled qubits in quantum teleportation transmit the state of one qubit to another distant qubit without any physical transfer of information. In quantum teleportation, qubits, tiny units of quantum information, become entangled, forming a special connection that allows information to be transferred between them. When you perform a specific quantum measurement on one qubit, it instantly affects its entangled partner, allowing the state of the first qubit to be recreated in the second qubit, no matter how far apart they are. This process leverages the principles of quantum mechanics, showing that information can be transmitted instantly across distances through the entanglement connection, making it seem as if the information teleports between the qubits. Quantum teleportation of information between distant qubits is thrilling because it promises to revolutionize communication, allowing for ultra-secure data transfer that's nearly impossible to intercept or tamper with. This capability lays the groundwork for advanced quantum networks and a future quantum internet, potentially transforming how we connect and share information on a global scale. Additionally, it provides a powerful tool for testing fundamental quantum principles, enhancing our understanding of quantum mechanics. Quantum teleportation also plays a crucial role in developing quantum cryptography, offering the potential for unbreakable encryption methods. By enabling remote quantum experiments and processes, it opens up new possibilities for scientific research and technological innovation, making it a cornerstone of future advancements in quantum technology. The visionary future of quantum teleportation envisions a world where quantum networks seamlessly connect global quantum computers, creating a robust quantum internet that enables instantaneous, secure communication and collaboration across vast distances. This network could support the development of unprecedented computational power and advanced quantum algorithms, transforming industries from cryptography to materials science. Quantum teleportation may also lead to a new era of distributed quantum computing, where resources from multiple quantum processors are pooled to tackle complex problems beyond the reach of classical systems. Before we can teleport information, we need to understand its fundamental building blocks, qubits. These tiny units of quantum information are the cornerstone of quantum computing and teleportation. In the classical world, information is stored in bits, which can be either a 0 or a 1. This binary system is the foundation of all classical computing, from the simplest calculators to the most advanced supercomputers. Think of a light switch. It's either on or off. This simple binary state is easy to understand and has been the bedrock of computing for decades. Qubits, on the other hand, are like dimmer switches. They can exist in a state that is not just on or off, but anywhere in between. This flexibility is what gives qubits their incredible potential. They can be in a state of 0, 1, or a mind-boggling combination of both simultaneously, thanks to the magic of superposition. This means that a qubit can perform multiple calculations at once, vastly increasing computational power. Imagine a spinning coin. Until it settles, it's both heads and tails at the same time. This is a simple analogy for superposition, where a qubit exists in multiple states until it is measured. That's the essence of superposition. It's a fundamental principle of quantum mechanics that allows qubits to be incredibly powerful and versatile. This ability to inhabit multiple states simultaneously gives qubits immense computational power. It allows quantum computers to solve complex problems much faster than classical computers. While a classical computer crunches through possibilities one at a time, a quantum computer, armed with qubits, could explore all possibilities at once, exponentially accelerating problem solving. This parallel processing capability is what makes quantum computing so revolutionary. But the strangeness doesn't end there. Quantum mechanics is full of phenomena that defy our everyday understanding of the world. Qubits can also be entangled. This is a special quantum state where the properties of one qubit are directly related to the properties of another, no matter how far apart they are. This means that two or more qubits, even separated by vast distances, become linked. When one qubit is measured, the state of the other qubit is instantly known, regardless of the distance between them. Measuring the state of one instantly determines the state of the other, no matter how far apart they are. This instantaneous connection is one of the most intriguing aspects of quantum mechanics. It's as if two coins, flipped miles apart, always land on the same side. This phenomenon, known as quantum entanglement, challenges our traditional notions of space and time. This spooky action at a distance, as Einstein famously called it, is the secret sauce that makes quantum teleportation possible. By leveraging the principles of superposition and entanglement, scientists are working towards the goal of teleporting information instantaneously across vast distances. Quantum teleportation is not about moving physical objects, but rather about transferring information from one place to another without traversing the intervening space. This could revolutionize communication and computing in ways we can only begin to imagine. The journey to practical quantum teleportation is still in its early stages, but the potential is enormous. As we continue to unlock the mysteries of quantum mechanics, we move closer to a future where teleportation is not just a concept from science fiction, but a reality. The stepping stones to teleportation are being laid today, and the possibilities are as vast as the quantum realm itself. Join us as we continue to explore and push the boundaries of what is possible in this exciting new frontier. Classical versus quantum, two worlds of information transfer. In our everyday lives, we interact with the classical world of information transfer constantly. From sending text messages to streaming videos, classical information transfer is the backbone of our digital age. We're used to information traveling in the classical world. This world relies on well-established principles of physics and electrical engineering to move data from one place to another. When you send a text message, your phone encodes your words into electrical signals. These signals are a series of ones and zeros, known as binary code, which represent the text you typed. These signals travel through wires and cell towers, ultimately reaching your friend's phone, where they're decoded back into text. This process happens incredibly fast, almost instantaneously, allowing us to communicate in real time. The information itself is copied and transmitted. Each bit of data is duplicated and sent through various nodes in a network, ensuring that the message reaches its destination intact. Quantum teleportation, however, operates on entirely different principles. Unlike classical information transfer, which relies on physical media to carry data, quantum teleportation uses the strange and fascinating properties of quantum mechanics. It doesn't involve physically transporting the qubit or copying its information. Instead, it uses a phenomenon known as quantum entanglement, where two particles become linked in such a way that the state of one instantly influences the state of the other, no matter the distance between them. Instead, it leverages the power of entanglement to transfer the qubit's state, its defining characteristic, without any physical transfer of matter or energy. This means that the information about the qubit's state can be transferred instantaneously, defying the classical limits of speed and distance. Imagine you have a pair of entangled gloves, one sent to a friend far away. The gloves are entangled in such a way that knowing the state of one glove immediately tells you the state of the other. You reach into your box and discover a right-hand glove. This simple action reveals the state of the glove you have, and by extension, the state of the glove your friend has. Instantly, you know your friend has the left-hand glove even before they open their box. This instantaneous knowledge transfer is a key feature of quantum entanglement and is what makes quantum teleportation possible. No information about the glove itself traveled between you, only the knowledge of its state. Quantum teleportation works similarly. The actual qubit doesn't move, but its state is transferred, allowing for a new form of information transfer that could revolutionize technology. It's about transferring the handedness of the qubit, its quantum state, not the physical qubit itself. This subtle but profound difference opens up new possibilities for secure communication and advanced computing. This distinction is crucial to understanding the power and potential of this revolutionary technology. Quantum teleportation could lead to breakthroughs in fields ranging from cryptography to quantum computing, fundamentally changing how we process and transfer information in the future.